I will be talking about transverse cracking in metal ceramic composites with lamellar microstructure. And this is research that I was working on with Romana Fiat from Darmstadt University of Applied Sciences and Igor Bus from University of Aberdeen. So metal ceramic composites with lamellar microstructure are a novel class of metal ceramic composites which are produced using an innovative technique called ice templating or freeze casting. So that technique involves taking ceramic suspension and freezing it. And as ice crystals grow, they push ceramic particles around, and layers of ceramic layers are formed, and porous preform is produced when ice is sublimated and freeze-dried. And after freeze-drying, this open porous preform can be infiltrated with molten metal or polymer. In our case, it was aluminium alloy. So it is infiltrated with the molten aluminium alloy using a squeeze casting technique, and a composite is produced in which metal has replaced frozen water. So this method produces composites with high ceramic content, and the method is very cost effective, so such composites might be of interest to automotive and biomedical applications. But because of the way they are produced, because the manufacturing and fabrication are driven by ice, the physics of ice, these composites exhibit very complex microstructure, hierarchical lamellar microstructure. So this is a schematic showing you what's going on here. So we have domains in which metal and ceramic lamella are parallel to each other, but these domains are oriented at certain angles to each other. And depending on the freezing temperature, we may have a fine microstructure or a coarser microstructure, and you can see from these photographs regions of parallel lamellas, and then lamellas at a different orientation in another area. So to investigate behavior of these composites, single domain samples were cut out of the composite and tested. So you can see these single domains and samples cut out of them at different orientations relative to the freezing direction. And because the amount of material produced was quite small, samples were made for compressive testing, and they were compressed a different direction relative to layer orientation. And this series of photographs shows you what happens to the layers when the material is loaded. So this is a stress strain curve, and each of the points highlighted with the letter has a corresponding photograph showing what's going on here. And if you look at photographs, say F, G, H, and I, you will see cracks appearing in ceramic layers. And this is a figure giving you a summary of a number of cracks in metal and ceramic layers at different stages. So let us focus now on one of such photographs and have a closer look at these cracks. So whiter layers are ceramic and gray layers are metal, and we see cracks which are spaced at some distance from one another, and some of these cracks look more like gaps, so it is not a mathematical section but rather like small holes. So all of this was our motivation for modeling. And we started with looking at this simple configuration, a ceramic layer between two metal layers. And ceramic layer contains a number of cracks transverse to the plane of the laminate. So we assume for modeling purposes that cracks are spaced uniformly and that they span the whole width of this sample. And because of that, we are able to model a representative segment of the sample bounded by two cracks, as shown here on the left. So these are cracks without crack widening, and this is a sample containing two cracks with crack widening. So cracks are actually like rectangular holes in the sample. So this is how we perform stress analysis of the sample. We average stresses across the thickness of the layer and width of the sample and produce these tilde stresses. And we have equilibrium equations for ceramic layer and for the whole sample. In terms of these microstresses, we assume that crack surfaces are stress-free. And when we write our equations in terms of microstresses, we end up with tau1, tau2 interface shear stresses at the metal-ceramic interface. So to solve equilibrium equations, we need to make an assumption about these interface shear stresses. So we assume that out-of-plane shear stresses vary linearly through the thickness of ceramic layer and metal layer. But we also assume that in the outer layer, outer metal layer, this variation of out-of-plane shear stresses is restricted to the shear layer. So it is non-zero here and then zero in the outer portion of the metal layer. So this is how it's written in mathematical way. And this allows us to integrate constitutive equation and obtain expressions for out-of-plane shear stresses tau in terms of coefficients k, shear-like parameters, and in-plane displacements in the metal and ceramic layer. So we also use constitutive equations for ceramic layer and for metal layer. And this allows us to solve our equilibrium equations and arrive at the following expressions for stresses in the ceramic layer. So sigma 2 stress in this direction and sigma 1 shear stress in plane of the sample. So here is how these stresses vary along the length of the sample. So stress value is normalized by the applied stress and shown for a range of crack spacing. So when cracks are further apart, we have this typical profile with a plateau, and then near the crack surface, the stress goes down to zero. When cracks are closer, the magnitude, the maximum value decreases, and the average stress takes this parabolic shape. But to know more, we need to perform a finite element analysis, and in that we uncover some interesting details. For example, that this black region near crack surface of about which I will talk in a minute. So when we take into account this is comparison of analytical predictions and finite element results. So we found that they are in a good agreement with each other, so our analytical model is okay. And this is when we take into account crack widening, and we see that when crack widening is taken into account, the maximum stress value is reduced. Finite element analysis allowed us to see the emergence of this compression region next to the crack surface, and as cracks spacing becomes smaller, this compression region goes in size, and as you see, for smaller crack spacing, it covers the whole length of the representative segment, meaning that new cracks cannot appear here because of the compressive stresses. So when we look at out-of-plane shear stresses, we can investigate further this shear layer assumption that we made and establish more accurately the width of that shear layer. Now, knowing stresses in the cracked metal ceramic composite sample, we can estimate stiffness properties of the ceramic sample. And for that, we use the equivalent constraint model. Generally, we assume that when a series of parallel cracks is present in a solid, this will lead to changes in compliances of that solid, and these would be compliances that will change. Only our solid is not infinite as shown here and as was used in these classical models. Our solid is a layer squeezed between two other layers, so we need to take into account that constraint effect of the layers on the cracked layer, and that's what equivalent constraint model allows us to do. Stiffness matrix of the cracked ceramic layer can be represented in this form. So Q hat is the stiffness matrix of undamaged ceramic layer, and the matrix that is subtracted from it contains stiffness properties of the ceramic material, and these two functions, lambda 22 and lambda 66. So they are called in situ damage effective function. So they account for damage in an effective manner, and in situ refers to the fact that they take into account that layer with cracks is situated between two other layers. So for these in situ damage effective functions, we can derive the following analytical, closed form analytical expressions that give them in terms of material properties of metal and ceramic, and also in terms of two damage parameters, D, which is the relative crack density, crack spacing normalized by the layer thickness, and GW, that is a relative crack widening, so width of the crack relative to the length of the segment. And knowing these functions, we can estimate stiffness properties of the equivalent homogeneous layer that has replaced that can replace the cracked ceramic layer. So to validate the model, we again used our finite element simulation. So the results in this table show the reduction ratio for Young's modulus of this composite as a function of relative crack density, which varies from 0.1 to 0.8. And this is the reduction ratio for the Young's modulus as predicted by the equivalent constraint model, the analytical model, and the finite element simulation. And you can see a good agreement between two approaches. So say for relative crack density of 0.1, the reduction ratio is, say, 0.78, meaning that composite with such density of cracks has lost 22% of its original Young's modulus value. And when crack density increases, that reduction can be quite significant, as the numbers here show. So How will crack widening contribute to stiffness reduction? So here is a reminder of the photograph with cracks in the ceramic layer, and these are cracks that are quite wide because once crack formed, the metal layers allows crack edges to move apart. So this is a representative segment containing crack with widening. So it's not a symmetrical section, but a crack of finite width 2L. So in this case, crack widening is 10%, and these are the crack widening used in the table. So the table gives you three material properties: Young's modulus, shear modulus, and Poisson ratio as a function of relative crack density. And for each property, we have prediction without crack widening and prediction with crack widening. And you can see from these results that when we take into account crack widening, the stiffness reduction that cracks post becomes greater. So if, say, for relative crack density of 0.2, Young's modulus is reduced by 36%. With crack widening, it becomes a reduction of 43%. So when cracks are present in the ceramic layer, a composite loses some of its stiffness, and this needs to be accounted for in when this material is used in applications and crack may develop. So to conclude, the model that I presented can successfully predict stiffness properties on a single domain sample, and it can be incorporated into a final element model of a multi-domain composite to predict stiffness of multi-domain material. But of course, our model and analytical and FE are theoretical, so we need more experimental data for such materials to validate our predictions. So that is our future work. So thank you for attention.